All right, real quickly, let's do a rundown of the stuff we've covered so far. Okay, different types of waves. We've talked about transverse versus longitudinal, right? What's the kind of waves that go through fluids?
Transverse.
No.
Transverse.
Hold on.
That goes through. Surface waves aren't possible.
Okay, shh. All right, obviously we're not paying attention. Listen. All right, in a fluid, because the molecules are not connected, you can't have a transverse wave, right? So inside of a fluid, gas or liquid, you can only have longitudinal waves, right? Now, there is one exception, and that one exception is at the surface of the water where you have surface tension. You have a combination of the two, which is called a surface wave, which has a circular vibration instead of a transverse or longitudinal type, okay? Yes, that's correct. All right. We have, let's see here. We talked about frequency equals 1 over the time period and vice versa. We talked about the velocity of a wave is equal to the change in distance over change in time. But for a wave only, we have velocity equals frequency times wavelength. Now, remember, everybody, that this does not mean if you double the frequency, you double the velocity. Okay. Remember, what determines the speed of the wave? The medium determines the speed of the wave. So therefore, if the frequency changes, the wavelength will change to keep the same velocity, unless you change the medium, right?
Yes.
Okay, we talked about the velocity of waves in a string, which were, what did I finally put? F equals, or F over mass per unit length, square root, right? This is the mass per unit length. Sometimes this is given the letter mu, this part. But that's the force or the tension. I think we wrote tension, didn't we? Yeah. I'll put tension up here. Okay, tension divided by mass per unit length gives you the velocity in a string. Okay, did I give you the equation for velocity of sound and air? I think we talked about it not being exactly constant depending on the temperature, right? But it's 332 plus 0.6 T. I thought I wrote that on the board.
Yeah.
Temperature in degrees Celsius. Or did I say 331.5? Okay. 332 or 331.5 if you prefer. Okay. And T is temperature in degrees, right? It's not time period. All right, so that's velocity of sound.
And it's in Kelvin?
In
and it's
air.
in Celsius, not
It's
Kelvin?
in Celsius.
Yeah.
So that's temperature in Celsius. Okay? All right, we talked about Doppler effect. Remember, Doppler effect happens whenever the observer or the source of the sound are moving. And you have to have a relative velocity between the two. Okay? For Doppler effect, we said the frequency that you hear or that is perceived, and sometimes did I write it with a prime? There are different ways to write it. Oh, I think I wrote O for observed, right? The frequency observed equals the frequency of the source times 1 plus V naught over V over 1 minus V source over V, right? Okay. Key thing to remember is that velocity is constant for the velocity is positive for the observer or the source if they're approaching each other, right? And they're negative if they're going away. So it's possible for one to be positive, one to be negative if they're going in the same direction, right? Because the one that's going away from the other is negative. The one going toward the other is positive. Okay? All right, so we talked about that. We talked about wave superposition, right?
Yeah.
That when the waves meet, they create a new shape. But the energy is neither created or destroyed when they meet. It just changes the shape of the wave. So you have two types of this superposition or interference. You have constructive. And you have, so this would add up to a bigger wave when they meet. or you have destructive, oops. And the way I have this one here, this one's bigger than this one, right? So when they meet, you're going to end up with a wave that's smaller than this one, because that one's going to take part away, right? That's still called destructive. So constructive or destructive interference, all right? We talked about diffraction. When a wave approaches a boundary like this, that these waves will bounce off. You know, like if this is a water waves coming up towards a seawall, and these waves will not just go straight past. They will bend around the corner, right? So they'll go around like that. And if you have an opening like this, then they'll bend around both ways. All right? All right, that's called diffraction. We talked about that. We talked about when waves meet, you get this interference, and we had a special case of one where we had two waves that were overlapped. And when you added them together, you would get this thing that looks like this, right? The two waves added together, and you'd get a loud, soft, loud, soft, loud, soft. And if this was light, it would be bright, dark, bright, dark, bright, dark. And if it was water waves, it would be big wave, smaller wave, big wave, smaller wave, right? And this is called beats. And we had what was called a beat frequency. And that's the rate at which this wobble in the sound occurs, right? And that's frequency 1 minus frequency 2, and you take the absolute value. We talked about how musicians use this to tune their instruments.
Oh yeah, we did.
And we talked about standing waves and resonance. That there are a couple of types that we see a lot. Some of you may have experienced this in the real world. Every object has what's called a natural frequency. It's a frequency it will naturally vibrate at. Actually, it has multiple natural frequencies. Okay? There will generally be a lower frequency. That's what's called its fundamental frequency. And then there will be higher frequency natural frequencies. All right? Like for instance, how many of you either have a car or been in a car where you go and sit at a stoplight, and when you sit at the stoplight, like the steering wheel vibrates really bad, or at certain speeds the car has a buzz to it or a vibration in it? Anyone have that going on?
I know my Mustang, right? Like if you stop.
Yeah, it's like and then, if you just take your foot off the gas or something, or take your foot off the brake, it goes away sometimes. Okay, what this is a natural frequency of part of the vehicle. All right? It's a frequency that naturally wants to vibrate at, and the engine happens to be turning over at that rate, and it causes it to go into this large amplitude vibration. Okay? It's called a natural frequency. And if you drive an object at its natural frequency, the waves will build up as they reflect back and forth inside the object. And you'll get that large amplitude vibration. Yes?
Isn't that how, like, opera singers break glass?
That's exactly right. So what they do is they input a frequency that is the same as a natural vibrating frequency of the glass. So the wave vibrates back and forth and gets larger and larger, just like it did in that string we did. And if it gets large enough, it can shatter the glass.
But isn't that like almost impossible?
It's very hard to do. You have to have a very strong voice, and you have to be able to hit that right note. I've actually seen it happen. They had it on MythBusters, by the way.
Yeah, I saw that on
You see the one on
MythBusters. It was
MythBusters?
hogging the most.
Yeah. Yeah, and you see the glass going back and forth, and all of a sudden, and it's like right up next to that guy's face. Like, don't wait for a piece of glass to find his mouth. Yes?
Yeah, there's like our commercial saying that they use deconstructed waves to kind of battle out that sound of your car. And like, is that really like they're doing? They're barely coming out with that?
Yes. For instance, most of you are familiar with sound cancellation. Bose was one of the first ones to come out with this. It's the earphones that you can put on, or the earbuds or whatever. And what it'll do is it will take the ambient sound wave. So the sound wave that's coming from outside might look like this. Okay, this device reads it in, and it pumps out this sound into your ear. Okay, now look. Crest, trough. Trough, crest. So when I add these together, what do I get? I get nothing. And so what they're able to do is take a sound wave that's repeating itself, like background noise, like the hum of the air conditioner unit, or like on an airplane, the hum of the engines, which is a repetitive sound. Takes it in, reads it, flips it over, cranks it into your ear in phase with the outside sound wave, and it deadens the sound. So by making more sound, it makes it quieter. Which is pretty slick. They do this in industrial factories where they have a lot of repetitive sound. What they'll do sometimes is they'll set up speakers next to the machine that's making sound that they can only get rid of so much of the vibration, right? And they'll put a speaker next to it, and the speaker will crank out the opposite wave, flipped over, of the wave that this machine is making, and it deadens the sound in the factory. Now, it's easier to do this for long wavelength waves, bass sounds, okay, lower pitch sounds, because the waves are longer. Remember, it takes some time to read the wave and then reproduce it. It can't happen instantaneously, right? So, if the wave is really long wavelength, it gives them time to make the inverse of that wave before the wave is already passed. Does that make sense? Okay, so it's a little bit easier to line them up for bass waves. And so it takes out the low-end sounds easier than it does the high-end sounds. I mean, you can do this with light as well. All right? Where you could, in theory, you could take like a laser beam. There's a certain frequency. You could shine the opposite wave of it right on top of it, and it should show no light. All right?
Let's try this. How much would it cost to do it?
In what?
How much would it cost to actually do it?
I have no idea.
It'd be really hard because the light's so fast.
Yes, it would be hard to line it up. Would be the hard part, I would think. I wonder if they've tried it up.
Just use the laser system to line it up.
Right. Okay. So interference, standing waves, resonance, and then we took standing waves and we applied that to a couple of things. Now, musical instruments, you want them to go into resonance, okay? But it's resonance where the device will vibrate to produce a lot of sound, but not break, okay? Not like when you're singing opera singer with a glass and the glass breaks, right? But it's a similar thing. The shape of musical instruments are so that they will resonate to produce extra amounts of sound, okay? Because the more air they're in contact with and the more that contact with air vibrates, the louder the device can be. All right? And then we talked about strings. First harmonic, second harmonic, third harmonic, and so forth in strings where you have fixed on the ends, and this is the length. And you can relate the length to the number of wavelengths, right? Like for this one right here, the length is L. How many wavelengths do I have here? I got 1.5, right? Yep. 1.5 wavelengths. Therefore, my wavelength is L over 1.5, right? So you can figure out what the wavelength is. If you know the frequency it's vibrating at, then you would know the velocity of the wave, right? Okay, so you can figure that out for fixed strings. And then we had two types of pipes. Generally, these are just called open pipes, but technically they're an open pipe. They're open on both ends.
WOP.
Okay, for a pipe. Okay, and these they're open or free on the ends. And if they're free on the ends, then you're going to have an antinode on the ends instead of a node on the ends, right? And so you can fit these types of waves in. All right, so tell me, this one right here, which harmonic is this?
Third. No, second. Right?
It's the second harmonic. Because there's the first harmonic. That's where the length equals 1/2 of a wavelength. And here the length equals 2/2 of a wavelength. And here the length equals 3/2 of a wavelength, right? And so this is the first, second, and third harmonic. Right? And then you can relate that to, if you know the frequency that's being driven in there, or the speed of sound, you can find the frequency. Right? So we can do that. And then we had the oddball, which was the closed pipe. The closed pipe is really an open closed pipe. It's open on one end and closed on the other. So fixed and free. So you're going to have a node over here and an antinode. Okay, so it's going to look like that. Where over here we have antinodes on the end. All right? Fixed and free, node and antinode. Okay? And so this is length equals 1/4 of a wavelength. And over here, when we go to the next one, it's going to look like this. That's the next higher frequency up, right?
Yeah.
So the length is equal to 3/4 of a wavelength. So we end up with the first and then the third harmonic because we have odd numbers here. First, third. Instead of 1, 2, 3, we have 1 and 3, and then the next one will be 5. Because what we end up with is there's my 1/4 of a wave, and then this from here to here is a 1/2 a wave, right? Okay, so there's our geometry there. Now, I will tell you one thing. What we just did is an approximation for the pipes. For the strings, we know exactly where the nodes have to be because it's locked down. For the pipes, the antinode actually does not occur right at the end. Okay? It doesn't occur exactly at the end. So this is approximately. Okay? Now there is a way to know exactly what the wavelength is going to be.
Yeah.
All right? And the way to know exactly what the wavelength is going to be is there's a lab that you can do. I don't know, did you do this lab?
Yes,
The one with the water? All right.
Wait, is he in the video?
Okay. This is if we have one frequency here, the fundamental frequency, and then we have frequency 2 and frequency 3, right? Where this is frequency 1 and this is frequency 3, right? 3 times the original here, and this is 1, 2, 3 here. All right, now, if you keep the same, like tuning fork, okay, if I put a tuning fork over this one right here and vibrate this thing, and I set up a wave, the first one I'll reach is this one, right? But what if I keep pulling this pipe out? There will be another spot where I will hear the loud sound, right? The resonance frequency. And that will be when I reach, how far out?
3/4 slammed up.
The next one I'll get, if I keep pulling this thing out, is I'll get one at when it's out here, and I have my original quarter wave, right? And then another entire 1/2 of a wave. Are you okay with that? Because what happens is I don't get another one until I have 3/4 of a wave. And this time my wave is staying the same length because I have the same air, I have the same frequency, therefore the same wavelength in both cases, right?
And then you keep having to add 1/2 a wave every
So I keep having to add a 1/2 a wave to get to the next one. Everybody see that? Okay, now, this is the way to find out exactly with pipes
one.
how to find the exact wavelength. Because this length here is approximately 1/4 of a wavelength, right? And this length from here to here that length is approximately 3/4 of a wavelength. But you know what? The difference between this one and this one is going to be exactly a half a wavelength. Why is it going to be exactly half a wavelength? Because from this point, from here to here, that has to be exactly a half a wave, right? Because it's node to node. I don't know exactly where the antinode is up here, but I do know that that point to that point has to be exactly half a wave. Oh, here, I got the... Okay. So, everybody, if they only give you the first length, then you're going to use it. Calculate the wavelength and the frequency, because that's all you got. But if they give you two lengths like this, to get the best answer and to get the most credit, you would subtract whatever this length is from this length, and that happens to be, if this is L1 and this is L2, then L2 minus L1 will always equal exactly 1/2 of a wavelength, and that is your best answer. That make sense? And let's talk about the last kind of interference pattern. It's called double source interference. All right, double source interference. Here's how this works. Okay? We have one speaker here and our other speaker here. We're going to call the distance between them D, because D is easy to remember. Okay, you have two speakers. Each one is putting out their own sound wave, which we could draw them again like this if we wanted to, right? But I'm going to draw it a little bit different this time. Instead of drawing these waves coming out like this, what we're going to do is just show the distance out away. All right? So I'm going to draw a line of symmetry down the middle. And then I'm going to draw a plane perpendicular to the line of symmetry. Okay? So this distance from here to here will be L. Okay? The distance up and down, we could call Y, but most of the time in the books they call it X. So this is going to be X equals 0, and it'll be positive up this way and actually positive this way. So it's going to be symmetrical. So X is measured positive in both directions. All right? So it's going to be symmetrical on either side. All right? Now, here's the deal. Does everybody see this distance from here to here? Okay? Call that distance D1 and D2. Everybody see that D1 and D2 are the same. Okay? If those two distances, D1 and D2, are the same,
Then you're in the middle.
then you're in the middle. And if those two speakers are putting out the same sound, they're hooked up to the same source, right?
What's the highest? What's the loudest?
So very good. This will be a constructive interference location. Why?
It's because all across that point the waves are meeting.
Yeah, the waves are in phase all the way there, and they're going to meet crest-crest or trough-trough, right? So they're going to be really loud here. This will be a place of constructive interference. This is called the central maxima. So it's a constructive interference spot. Yeah, maxima is a constructive interference location, all right? Now, but wait, what if you're not right there? What if you're up here? Under what conditions will we be up here somewhere above, and we will also get another constructive interference location? Will D1 and D2 be the same?
No.
Ooh. So when will the waves line up again to produce constructive interference?
2x.
When the difference between
1,
is
2,
What's half?
3,
when it's one way.
4, Here, let's do 5, okay? Well, this one can't go 5 wavelengths there, but when will it get there and they'll still be in phase?
6.
When it goes 1 extra. So 1, 2, 3, 4, 5, 6. If they both meet up, when I go exactly 6 waves instead of 5, they'll be lined up again, right? It's like sine waves. If I put sine waves next to each other, and then I shift one of the sine waves off exactly 1 wave, do you see they're going to line up again? Crest, crest, trough, trough. Okay, so that's the key. This is called, this spot right here is called the central maxima, and that is, oh, no red marker. Use brown, I guess. This is n equals 0. Actually, n or do they use m? I think they use m. Yeah, they use m. M equals 0. I guess that's for maxima 0. This will be maxima number 1. And what does the 1 stand for? The 1 stands for that they are exactly how many wavelengths off in path length? 1 wavelength off. This means that they are exactly 1 wavelength path. What are you doing?
Nothing.
Exactly 1 wavelength path difference. All right, now let me redraw it one more time, and then we're going to talk about the geometry of this thing. Okay, so we're going up to this spot, which will be maxima number 1, where you're 1 wavelength off. Okay, this is D1 and D2. All right, you ready? I need a new color here. I'm going to have 2 triangles here. Okay? I'm gonna go like this. Okay with that?
Yeah.
Where this is now an isosceles triangle. And which leaves me, when I have a little triangle down here,
How do you know it's isosceles?
I just made it isosceles.
You're making it. Purposely making it.
Ooh!
I just made it isosceles. All right? You see this difference? If this right here and this right here are the same length, then how much is this again? D2 minus D1, which happens to be exactly some multiple of a wavelength, right?
Oh, yeah.
Right? It has to be exactly, in this case, 1 wavelength, right? All right. So does everybody see that this is theta right here? I'm going to make that theta. So therefore, the sine of theta equals what? Opposite, which is m lambda over d, the hypotenuse. Got it? There's our geometry right here. That when I draw this triangle, make this isosceles, that I end up with this is my hypotenuse and this is my number of wavelengths path difference. And that's going to be some multiple of wavelength. And so sine of theta is opposite, which is d2 minus d1, which is m lambda, over the hypotenuse, which is d. Okay, so here is our first equation for double source interference. It's right here. It's sine of theta, d sine theta equals m lambda. It's the way we normally write that. Now, this will be good for whether it's speakers, or whether it's light waves, or whether it's water waves in a wave pool. It doesn't make any difference. Any kind of wave. All right. Now, we're going to do one approximation. Okay, you ready? Do you see this triangle right here? If I start in the center and I go up, split the difference right there, go down and across. Everybody see that triangle?
Yeah.
The nice green triangle or teal triangle?
Theta will be the same.
These two triangles will be similar.
Oh, that's.
Which triangle? Which triangle?
This one and this one. They're similar triangles. Okay. This triangle, similar. Shh. Does everybody see that the tangent of theta in the big triangle will equal what?
Distance.
It will equal this x right here, right?
Come on, hook me up with a blue.
X sub m, whichever one you're talking about, whether you're talking about the first one or the second one or whatever, divided by L, right? X sub m divided by L. So like the distance to this spot would be x sub 1. The distance to the next one will be x sub 2.
And are they
Okay? Now, if, have you ever done small angle assumption in a math class? You know what that is? Okay. See this triangle right here? Where that's theta, and this is x, and this is h, and this is here. We'll do this as y. Sorry, y and x. Sine of theta equals y over h. Tangent of theta equals y over x.
Agreed.
Agreed?
Agreed.
If theta is small, then sine of theta is almost the same as tangent of theta.
I'm gonna assume it's almost.
Because h and x are nearly the same length, correct? You don't like where this is going? We are making
Y
assumptions.
is also very short.
Oh, big X. Big X, X1.
And then you first divide it out.
Over here, hang on, that x is with this. All right, this is called a small angle assumption. When does this assumption start to break down? Okay, if it's less than 5 degrees, piece of cake, no problem. 10 degrees or less, a lot of times that's where we stop. If it's more than 10 degrees, this approximation starts to go south and not really work very well. So, look, if we assume if theta is small, then that means this equals this, which means xm over L equals m lambda over d. And we usually rewrite that to look like this. X sub m equals m lambda L over d. Now, put a little approximate sign over the top of that. All right? It's approximately equal. Your theta better be less than around 10 degrees. If it's more than 10 degrees, you cannot use this equation. Are there any limitations on the first equation? No. So why do we have the second equation if this one always works? Well, because this one is easier to measure. Because look what we have to measure in this one. All we have to measure is d, the distance between the speakers, L, the distance to our line over here, and x, right? It's all geometry measurements, right? Whereas up here we have to measure an angle, and sometimes we don't feel like it. All right? Now I want you to notice, if the angle is small, look what you get. If I go from 0, if this is 0, then I'm at what location? 0. If I'm at 1, I'm at which location? If I'm at 2, I'm at... How does 1 and 2, the locations of 1 and 2, differ from each other? 2 is double the distance of 1, right? Okay, so what you're going to get is you're going to get a repeated pattern that is nice and uniform, right? As long as the angle is small. Once the angle starts to get big, they start to spread out more. Okay? All right. So here's what
that gives you the distance of X between every.
Yeah. So if you just go from like if they ask you what's the difference or distance between the third and the fourth maxima, you could put 3 in here, figure that distance. Put 4 in here, figure that distance, and subtract them. Or you could just do 1, and that's the distance between 0 and 1, and that should be the same distance, right? Okay. Piece of cake. All right, now I want you to notice a couple of things. Here's the other thing that this is great for. Hang on, well, let me answer your question. Go ahead.
On the test, will they ever ask us to find the, since x isn't always constant with the large angle, would they ever ask us to do that?
Yes. Okay. So tell me this. If they give you a problem like this, where they say, by the way, that's an outstanding question. They say the distance here is 1 meter. And they say that you are 10 meters this way, and that you stand out here 4 meters. Let's make it 4 meters. Okay? You stand out here 4 meters, and they say, and you find your first maximum. So like you find a maxima here, it's loud right here, and then you walk up this way and it's loud again right here. And they say, okay, so what's the wavelength? All right, so we know that m equals 1 because I've gone from 0 to 1, right? So I know that's 1, and I know that distance, that distance, that distance, and you'll go ahead and plug the numbers in here.
Assume it's a small angle.
Well, is it a small angle? Oh, let's find out. Does that look like a small angle?
No.
No. All right? Unless this distance is much larger than this distance, so sometimes they'll do this. They'll say, L is much, much larger than X. If they give you that, then you're at a small angle. All right? But right here, what's our angle? What's the tangent? Theta equals 4 over 10. So what's theta? Somebody?
21.
21 degrees. Can I use the approximate equation? No. Guess what? If this is a multiple choice question, guess what? Answer choice A is if you used this one. The loser equation. And answer choice B is going to be if you use this equation. And that one is the best answer. So that one's correct, and that one will be wrong.
So are you telling us that on your test, if we get something like this, the answer is going to be B?
Or some other letter between A and E. All right? So there you go.
But it's definitely not going to be A.
Well, of course not. A's always a distractor,
Right.
unless it's the answer.
Touché.
No, but we can
So just be careful. Now, what this equation is really great for, though, is to show you what happens if you make some changes. Okay? First of all, let me show you what this will look like. Sometimes they draw what the distribution looks like. Okay? So like, for instance, if this is sound, if you go right down the center, you're going to get a loud spot. A lot of times they'll draw it and it'll look like this. Okay? So you get a loudest spot here, and then it'll go to nothingness, loud, nothingness, loud. But actually, it goes down in amplitude because it's loudest in the center than it is out here. Why?
Because it's always
Because
further.
it's further.
Yeah, because you're
from
getting
the-
further and further from the sound source, right? So you will get this loud, soft, loud, soft, loud, soft, but the amplitudes, the loudnesses start to drop off. Okay? Now, this is what it visualize what it would be like for sound, right? Because it's kind of hard to draw loudness, right? So this is the intensity. Very bright, very loud, not loud, loud, soft, loud, soft. Okay. What if we did this? What if we took this distance and we made it bigger? So we moved the speakers outward. How would that change this pattern?
Be further up at the ends. Like, it'd be more intensity.
Here's how you find out. Here's your equation. If I increase the distance in between, what happens to the spacing? Oh no, it gets smaller. Kind of counterintuitive maybe. They would move closer together. So if I move these out, what will happen to my pattern? Well, my pattern will now look like this. They'll be scrunched in closer, right? This distance between here is now only that distance, right? Scrunch in closer. Okay, what else could they do that would be different? Okay? What other kind of changes could they make? Could they change the wavelength?
That's if
That's a pain.
if it's fixed.
If what's fixed?
The
The screen, where you're standing, yes.
Yeah.
This is here. I just moved it over here so I could redraw it.
Oh, all right.
Okay? Well, let's do that. What if instead we increase the length? So let's say that we were right like this, but now we're going to go back here and see what the sound pattern looks like. They're just going to be further apart, right? Because the sound, these things are going to spread out as you go farther out, right? So you look over here, as the length to that location where you're measuring the sound increases, the distance increases. What happens to the wavelength? What if you play, instead of playing a 100 hertz note, you play a 400 hertz note? What happens? Okay, the frequency goes up, so the wavelength goes down. If the wavelength goes down, then the X goes down. In fact, it would go down by a factor of 4, right? Because I quadrupled the frequency, so the wavelength is cut by 1/4, or to 1/4. So this would be cut, the spacing would be 4 times closer together. Does that make sense, how you do that?
Yes.
Excellent. All right, now, that's for sound, and we kind of experienced that in the classroom. If we could have put those speakers out in the middle of a football field, and we could walk across in front of them, then we would really experience this, more so in the classroom. Because in the classroom we have echoes from the walls. Okay? The sound goes out and then comes back off the wall. Alright? Now this occurs in sound waves. But it also occurs in light waves. Okay? In a light wave arrangement, it's the same thing except this time you got light waves coming up like this. Now, this was one of the major arguments way back. There used to be a huge argument back in the 1600s and 1700s about what light was. And Newton was the biggest proponent back in the late 1600s of the particle theory of light, that light was a particle. And he could demonstrate all the different properties of light if light was a bunch of little bitty particles. Okay? And then there was a competing theory. And the competing theory was by a person named Christian Huygens. And Christian Huygens said that light was a wave. And he could explain, all the different properties of light, but light was a wave instead. Now, most people believe Newton for 2 reasons. Number one is Newton was more famous, and his theory was simpler. Okay? Huygens' theory was mathematically more complicated, and Huygens was not as popular, famous of an inventor or scientist. And so the debate went on for a long time. And one of the big debates of why light was not a wave was because you would see the interference pattern of sound waves and water waves, but they could not produce the interference pattern of light waves. Okay? And they said, well, of course, then light, you can't do it because light's not a wave. All right? So why couldn't they produce the interference pattern of light waves? Well, here's the deal. This distance here needs to be about the same size or smaller than the wavelength of the wave in order for you to experience, to be able to see that interference pattern. Okay? It's like sound waves are really long. So you can have 2 speakers out there, no problem. You can get that interference pattern piece of cake. But if I put a flashlight here and a flashlight here, okay, they're way too far apart for you to see this interference pattern. You've got to have your openings really tiny, close together. All right? And the other thing is they didn't have what's called a monochromatic light source. It was harder for them to get a monochromatic light source, which means one wavelength. All right? It's pretty easy to produce one wavelength of sound. Just get a musical instrument and play it. All right? But this was harder. So how close did they have to get these together? Well, remember, light, visible light, Roy G. Biv. Red light out on this end is the longer wavelength. It's about 700 nanometers. This end, violet light, on the shorter wavelength end, is about 400 nanometers. So you've got to get these openings really close together. Okay? For that to give you anything.
So if it's like, if there's a distance between those, would you only see a certain color?
That's correct. So like each one of these different wavelengths is a different color. And a different frequency, a different wavelength, but they all have the same velocity, which is the speed of light. That's correct. And the reason why we talk about wavelength instead of frequency is because that's a nice convenient numbers to remember instead of frequency. Frequencies are like, yeah, it's like 10 to the 14th hertz or something. I don't remember what it is. I have to look it up. But they're not nice convenient numbers. All right? So once they get these things small enough, guess what? They see an interference pattern. So Huygens wins. All right, so if you're over here now, and here's your distance L to the screen, and this is your X up and down, what do you see? You know what? I'm mad at myself. I left the lasers. I forgot to bring them. Because I could show you exactly what you
That
would
means
see.
you have to postpone the test.
No, I'm not proposed.
You see
postpone
more
the test.
intense and less intense.
What? Yeah, you would see brightness, darkness, brightness, darkness. Now, all right, if you just have two openings, what you'll actually see is, let me see, if it's green light, here, we'll do yellow. All right? What you'll see is a bright patch in here that will fade into darkness, and then it will get brighter again and be real bright. And then it'll fade into darkness, and then it'll get real bright again. And then it'll fade into darkness, and then it'll get real bright again. So you'll see this bright, dark pattern.
Oh, the white is dark.
Yeah, unfortunately my white is dark.
I know, as I was.
Here, we'll make it look like a bumblebee. Darkness.
Mr. Bowlers should be here.
Why? All right, so you're going to see light, dark, light, dark, light, dark. Okay? Same exact equation. Right? You go to the wave pool at Hurricane Harbor. The wave pool looks like this. It looks like this because you have one wave source here and one wave source here. And so what do? You get big wave, little wave, big wave, little... Oops, I should have put one right down the middle. There should be one right down the middle. So you get regions of maximas and minimas. Seashell. Or plane, yeah. All right. Okay, now, everybody, so it looks kind of like this. Here's x equals 0, x equals 1, x equals 2. I'm sorry, not x, but m. M equals 0, m equals 1, m equals 2, and so forth. M equals 1, m equals 2, blah, blah, blah. Okay, now what if you have 3 slits instead? Okay, you got a different pattern.
Just more.
What happens is you get this and then a little one in between. This, a little one this, a little one this, and a little one this, and a little one. Okay, what if you have 4? Then you go this and a little, this and a little, this and a little, this and a little. Now, what if you have lots and lots and lots and lots and lots of them? You know what you get?
A whole lot of this.
You get this. You get a bunch of really tiny ones.
Can't even notice.
You can't even notice them. And then a spike right there. And a bunch of little bitty tiny ones. And a spike right there. And then a bunch of little tiny ones. And a spike right here.
This is what we use.
Yeah, and this is called a diffraction grating. So this right here works for a double source, or sometimes they call it a double slit for light, because they'll have 2 slits and they'll shine light through it. So double source, double slit for light. And also for what's called a diffraction grating. And I apologize, I was going to bring it in and I totally forgot. Diffraction grating.
Mr. Grimm.
Now the diffraction grating has the exact same spacing. Hold on just a second. The only difference is that you have all these little ones in between that end up being darkness for light, and so you get a real spike. So if you shine a laser through a diffraction grating, what you get is this. Instead of this, pattern like this, what you end up with is, I'll use something you can see. If it's a diffraction grating, you'll get a dot, and then a dot, and then a dot, and then a dot for your pattern. Because all of this in between has been destructively interfered with.
Well,
Okay.
wouldn't it really be like a line?
If the light source is a
Oh,
laser,
yeah, it's
then it'll be a dot. If the light source is broader and you have two slits, then instead of it being a dot, it would be like a line, a line, a line, and a line. That's correct. Okay? Yes. 3D glasses have to do with polarization. Oh, Gerat, I forgot about polarization. Don't let me forget. I got to talk about that one. All right. So, this and this, diffraction grating and double slit or double source. There's one last one. You have to know these two. You have to know the geometry of them. Okay, there's one more. The last one is, what if you only have one opening?
Okay, so that's one with multiple. Is that polarization?
No, that's not polarization. Right. Okay, what if you only have one opening? Turns out, because the light will bend around this corner and bend around this corner, you'll actually still get an interference pattern. But the pattern's a little different. What you end up with is if you have just one opening, you'll get this. You'll have little one, little one, little one, little one, and then you'll have a great big double wide, then a little one, little one, little one, little one. Because most of the light goes straight
And
through.
those little ones keep decreasing.
Yeah, and they decrease like this. But they decrease really fast. So what you end up with, this is kind of weird, you end up with a central maximum that's really twice as wide as the rest of these, and it's very bright. Okay, that's all you need to know for now. That's actually what we see when we look through our fingers like this at the light source. What we don't see, but you can see the lines in between. Those little lines, that's these things that you're
Funny
seeing.
watching people doing
Little
that.
lines in between. Yeah, you can actually see it. It's pretty cool. Hey, by the way, and if you need glasses, all right, and you take your glasses and put them up like this, if you're farsighted, you need glasses that take the light and spread it out before it gets into your eye. Farsighted is you can see, no,
Yeah.
back. I said it wrong. If you're nearsighted, means you see things close up but not far away. You need glasses that spread the light out before it gets into your eye. All right, well look, if you do this, when light goes through the opening between your fingers, it spreads out. So if you are, I almost said it again, if you're nearsighted, you can go like this and put these fingers close together, and when you do, it'll make your vision better.
Wait, is that when you squint?
I can do this. When you're just blind, you can just do this.
That's why when you squint, if you squint like this, real thin, sometimes you can see fine, or you can just go like this,
This is so cool!
and you can see.
My sister just does this.
Oh yeah, and you can do that too.
Oh yeah. That's right.
That'll work. Oh, come on. That's not what we meant.
Because his sister does this.
That's right. No, we're not making a statement about people from the Asian part of the world. Okay?
Asian part of the world. What are you trying to say? Divide the world? No. What?
Stop it!
You said it.
No, I said nothing.
Uh-huh.
It's you punks. I mean, you. It's you punks. That's what it is. All right. Okay, polarization. Thank you for somebody. Daniel, did you mention polarization?
Yeah.
Here we go. Polarization.
Did something good.
All right. Okay. You're in jail. So here you are behind bars.
Like game.
All right? And I decide to send you a message on how I'm going to help you escape, right? And so
Sending code.
I send code through with a wave. And the way I do it is one way is I send a slinky through to you, like this, right? And I'm sending you Morse code through the slinky. All right? Now, I could easily send Morse code through the slinky by doing this, by pulling it back and letting it go, and I'd make a longitudinal wave, right? And it would go right through the bars, right? But if I'm going to do a transverse wave, I'm going to have a problem depending on which way I shake the thing, right? If I shake it up and down, like, I will be back at midnight, that's okay.
It definitely wasn't.
Midnight has 5 syllables.
I'm using shorthand.
Short.
But anyway, using short waves.
I will be back at midnight.
Yeah. Now, if I shake the wave back and forth like this, why is that going to be a problem? It's going to hit the bars. All right, now, there are devices. By the way, this device right here, this device right here, it will polarize transverse waves, but not longitudinal waves. Longitudinal waves are going to pass right through. But transverse waves, only the waves that oscillate this way and this way will get through. But the waves that oscillate back and forth will be destroyed, right? And when we talk about waves, polarization means that you let through these waves, but not these waves. Does that make sense? All right. Now, light waves are transverse waves. Okay? And the light waves, depending on which way they oscillate, this way or this way, have a tendency when they hit a surface to bounce off or be absorbed. Okay, you've all skipped a stone before, right? Across water? None of you? Oh, come on. You may not be very good at it, but how do you throw the stone?
Sideways.
You don't throw the stone like this. You throw the stone like this, right?
Down.
So that it skips instead of diving in, right? Okay, now the same thing is true of surfaces. If I shine a light on this board and it's oscillating up and down, when it hits this board, it's going to skip off. More likely to skip off. But if I shine a wave that's oscillating back and forth like this, it's going to be more likely to be absorbed and not skip off. Okay, so, everybody, when you're driving in a car, the road in front of you is this way. Right? So, the light that comes at you that bounces off the road surface is mostly polarized which way? These will go into the road and dive in, right? You want them to become like this and then skip off the road, right? Well, that's what they do, right? So the light that comes off the road into your eyes is mostly polarized back and forth this way, like this. Okay? Back and forth into your eyes. So, you want to get rid of that light. How do you get rid of that light? You have glasses that have either a crystal structure or a real structure inside that's like this. Okay? And so if I have a polarizer that lets through light this way, but it's oscillating back and forth this way, then all the glare that's skipping off the road now is destroyed. Okay, how many of you have polarized sunglasses? Okay, if you have polarized sunglasses, what I encourage you to do is to drive down the road on a nice sunny day,
Your head sideways.
and then go like this. Glare. No glare. Glare. No glare. All right?
I do that all the time.
Oh, drive on the opposite side of the road.
Yeah. Drive on the opposite side of the road. How would that help?
It'd be funny.
No, you drive a helicopter, you get flung sideways.
Glare. No glare. No glare at all. What the heck?
Lights out.
Yeah. No glare. All right.
No, see what you do is instead of tilting your head inside, you just turn really suddenly and drive on two wheels. That's what you.
Just to the car.
Okay. Now, so polarizers are devices that will kill or not let through light that's oscillating one way, but let light through that's oscillating another way. So that's what polarization is, all right? And polarization only works on transverse waves. Okay? Yeah.
You said that it's going like perpendicular, right? It's destroyed. How is
It's absorbed by the structure. So the structure, the material gets warmer, it becomes heat. That's correct. So like if I did this with a spring, the bars would get warmer as I'm whacking them, right? I'm hitting them. Okay. Any questions? I believe we've covered everything we need to cover about waves. I hope that it's going to be on this test.